Hello everyone, a warm welcome to all of you. So in this video I will show the simulation of NOMA in MATLAB. There I have covered the BER performance of user NOMA. At the same time I will show you how to do the SIC superimpose coding and the decoding at the respective users. All this step I will show one by one, and I guarantee you that if you follow this code you will be able to simulate any kind of NOMA system. So we need to configure some parameter at the transmitter side. So we'll generate binary data for user 1 user 2. For that we need to give the length of the data we need to consider. Suppose n is 1000, it is the length of data we need to consider for user 1 user 2. Then we need to give the distance of the respective users. So here user 1 is close to the base station, so its distance is 200 meter, and user 2 is the farthest side from the base station. Suppose its distance is 1000 meter. So here D is my distance matrix, which will contain distance of user 1 user 2. Now we need to give the power coefficient of the respective user based on their channel condition. Now here user 1 is strong user and user 2 is a weak user. So the power coefficient for user 1 suppose it is alpha 1, and power coefficient for user 2 suppose it is alpha 2. Now this alpha 1 should be less than alpha 2, as user 1 is a strong user, so we will give him the lower power. And alpha 1 plus alpha 2 comes to sums to 1, and this both alpha 1 and alpha 2 should be between 0 to 1. So all this condition we need to satisfy. So we have taken the power of user 1 as 0.3 and power of user 2 as 0.7. Now we need to give the range of power we want to consider. Suppose we will start from 0, we will increment with 1 and go up to 20, and this power is in dBm. So we will convert it in linear scale for our simulation. So this is a formula to calculate the dBm power to linear scale. Then we will calculate noise power. For the calculation of noise power, we need to give the system bandwidth. So here I have taken the system bandwidth at 1 MHz, and this is the formula for the noise power. Now again we need to convert this noise power in linear scale as it is in dBm. After that we need to blank matrix to store the bit rate of user 1 and user 2. That is why we have taken PR1 to contain the bit rate for user 1 and BR2 to contain the bit rate of user 2. Here BR1 contains the all bit rate for user 1 for all power, not SNR. It is power. Now for each power we will iterate our system. Now what is the number of iteration we want to consider? Suppose R is 500. That means for each power we will simulate our system for 500 times, and this iteration will give a overall better result. We will average and we will see what is the result coming. Now we will generate our binary data for user 1 user 2. So this is data generation of user 1. This ranti is a function which will generate random integer, and this random integer will be between 0 to 1 as we are considering binary data. This 1 is indicating only one row, and n is indicating number of data we want to consider. So n is our 1000. Similarly for user 2, same. Now we need to modulate the data of user 1, user 2. Here we will consider only BPSK modulation, right? So this is my function PSK mod. In the PSK mod, we are sending data 1 as first argument, and second argument is 2 is for only for the BPSK we are considering. That is why it is 2. And mod 2 is the modulated data for user 2. After that, we will run a for loop, and this for loop will take each power we are considering. Here the power range is from 0 to 20. So that is why the for loop I will start from 1, it will increment with 1 and go up to the length of pt. Here the length of pt is 21. It will start from 0 and go to 20. So that is why we need to consider the length of pt. Then this BR1 and BR2, I will explain why I have taken the BR1 and BR2 is 0 later. After that, as I have told you that for each power, we need to iterate our system. Now, R is the number of iteration we want to consider for each power. So that is why I have taken another variable J. It will start from 1 and it will go up to R, right? Now, after that, we need to design the fading channel for user 1 and user 2. Now, you know that for relay fading, here we have considered the relay fading channel. So, channel coefficient H is form is distance to the power minus n, where n is the path loss coefficient into x plus j y. This is the relay fading channel model, right? Here d is the distance. Here both x and y are normally distributed. Their mean is 0 and variance is 1 by 2. So we need to generate this channel for both user 1 and user 2. So here you can see H1 is the channel coefficient matrix for user 1 and SQRT square root of distance whole to the power minus 4. Here 4 is my path loss coefficient, and as you have here I have taken I am calculating the channel coefficient of user 1. So D1 is the distance of user 1. Then we need to give x plus j omega, and their mean will be 0 and variance will be 1 by 2. That is why here x is ran 10. It will generate random data or normally distributed, and total length we are considering as n. So 1 is the number of row, only one row, and n is the number of data we want to generate. Here we have taken that our data will be, the length of data is 1000. N is the length of data. So for each binary data, we want to consider one channel fading channel matrix, fading channel coefficient, right? So it is x plus j y. So y is also same, divided by SQRT2 to make the variance 1 by 2, right? And for user 2, this is the same. For user 2, I have calculated d2. d2 is the distance of user 2, and x plus jy plus divided by SQRT2, same. Now we need to generate the noise. Now for the calculation of the noise, at first we will give the noise power. It is SQRT n naught square root to n naught. N naught is already calculated here. Here you can see this is my n naught, and then we will generate random complex noise, right? So the form is same, x plus jy, and both x and y will be normally distributed with mean 0 and variance 1 by 2. This is the same thing. Then we need to do the superposition coding. Superposition coding of the data of user 1 and user 2, right? So at first we will give the power. So here the power matrix is pt, and at first we will consider the first index value of power. So I is already started from 1, so that is why pti. Then we will multiply the modulated data of user 1 with his power, and after that we will add with the modulated of user 2 multiplied with his power. SQRT C2 is the power of user 2. After that, at the receiver side, both the user will receive their respective signal. So y1 is the received signal at user 1. Now how to get this y1? Now, you know that for any wireless communication channel, the received signal Y is a signal multiplied with its channel coefficient plus noise. So T is my superinput signal. It will be multiplied with its channel coefficient plus noise. This is the form. For user 2, it is also the same. T is the transmitted signal because we have generated only one signal, only one superimposed signal, and this signal will be received at both user 1 and user 2 end. After that, reception at user 1. So when user 1 will receive a signal, at first it will do the channel equalization, right? So that is why the received signal is equalized with this channel, right? So here I have considered exact channel equalization. Otherwise, I need to estimate the channel. Then we need to divide. So that is why actually I have considered here exact channel equalization. So I have divided the received signal with this channel H1. Now after that, as user 1, here you can see is a strong user. So it need to eliminate the interference effect coming from the user 2. User 2 has higher power. So the received signal user 1 will have an interference from user 2. And this interference has higher power than the power of the signal of user 1. So it need to do the SIC here so that it can eliminate the interference effect coming from the user 2. So here I have shown you the SIC process, how the SIC will be done. So at first, what we will do, the user 1 do direct demodulation of the received signal, right? Now, after doing the direct demodulation, the demodulated data will be again modulated. Now, when it is modulated, we will get the user 2 signal, right? Now, this signal need to be multiplied with the power of user 2. Then we will subtract this signal from the new 1 1. New 1 1 is the received signal after channel equalization. So when we will subtract the user 2 data with the received signal data, then we will eliminate the interference coming from the user 2. And after that, we will do here direct demodulation. When we will do the direct demodulation, here we will get the data of user 1, right? Now, here the BR variable will store how many bits are different from the actual transmitted data, right? So BR1, as already I have configured initially at 0. So BR1 will be equal to BR1 initially whatever we have plus NNZ is a predefined function. It will give us the number of data which is different, right? So initially this is my decoded data at user 1 end, and data 1 is the actual data transmitted from the transmitter. So DCY1 not equal to data 1. So this overall function will give me the number of data which are different. Now I will store all this data in BR variable, and here I will iterate the whole system with r number of times. So that is why BR1 will be updated r times. Now for your simplicity, I will try to explain the SIC again mathematically. Uh, it will be good for you to understand the SIC mathematically. Now, so suppose receive signal at user 1 after doing the channel equalization y1 is sqrt p alpha 1 into p into x1 plus root alpha 2 into p into x2 plus noise, right? Now, this is my intended signal part and this is my noise part. So this is not noise, it is interference part, and this is my signal part. Now, user 1 need to eliminate this interference effect coming from user 2, and this interference has higher power than the signal power because alpha 2 is greater than alpha 1. So what it will do in the SIC, the SIC step, at first user 1 will directly demodulate this Y1. If he directly demodulate Y1, it will get the demodulated version of X2, right? Now suppose it is X2 bar. Now it will again modulate this signal, so it will get X2, right? Now it will multiply X2 with the power of user 2, which is alpha 2 into P, right? So we will get X2 into root alpha 2 into P. Now we will subtract this part with the receive part, right? So what we'll do is that after doing that, so alpha 1 px1 plus alpha 2 p into x2 plus noise part will subtract x2 into root alpha 2 into p. So this part will be eliminated, right? And we'll be left with alpha 1 into px1 plus a noise. So this is the SIC step we will do at the user 1 end, right? Uh, after doing the SIC, we will calculate the bit error rate and it will store in the BR variable. As this video is becoming lengthy, so I will make the second part of it, right? Thank you.